Section 8.8 is on page 508, talks about improper integrals. If you recall from the fundamental theorem of calculus, if you take the integral from a to b of f of x dx, the conditions were a and b were enclosed a finite integral, and f of x is continuous on a and b. That was the condition. So what are the exceptions? The exceptions would be if a and b are not finite, they're infinite, or if f is not continuous. So the first half of this section, these problems I'm going to do right now, are going to deal with what if those are not actually finite, such as if f is continuous, so this f is continuous on a to infinity, and I integrate from a to infinity. Well, this is one of the exceptions. Or if f is continuous on negative infinity to b, so this part is still defined, except now you have a negative infinity instead of a, which is a finite number, and b, which is a finite number. Or if f is continuous everywhere, and then you look at not 1 to infinities, 2 infinity, not 1 infinity, 2 infinities. So it turns out as long as f is continuous on this interval, then the integral from a to infinity of f(x) dx turn out to be, you would use a substitution of b for infinity, and you take the limit as b approaches infinity. Here you would take negative infinity out, put an a instead, and take the limit as a approaches negative infinity. And here, if you have positive to negative infinity, you break it up where c is any real number, and then you follow steps 1 and 2 for each of those. If one of those integrals diverge, you're done. And how would an integral diverge? Well, let's see how that works. Integrals with infinite limits of integration are improper of type 1. Type 1 when those are infinite. Type 2 when this is not continuous. 1 we dealt with, 2 we dealt with, and 3. So this is how you take the integral, but how do you make a conclusion? In each case, if the limit exists as a finite number, as an actual number, not infinity and not negative infinity, we say the improper integral converge. And if the limit of the value, is the value of an improper integral, if the limit failed to exist, if you get infinity or negative infinity, then we say the improper integral diverge. So I'd like to look at page 517 on few problems. Now, no need to squish all of those in. I'll just copy them in, but I want to do them in that order. Evaluate the integrals. I'm looking at problem number 2. Well, I know that this is the integral, and this is how we're going to get around it. We ignore the limits, so we don't write 1 to infinity or 1 to a, so that you're not carrying that limit as x approaches infinity with you. You integrate, and at the end you add the limit. That's an easy way of doing this. Add 1 to the power. If you take negative 1.001 and add 1 to the power, that's negative 0.001 divided by negative 0.001. I'm going to take this limit from 1 to a, and I'm going to take the limit as a approaches infinity. That is the limit as a approach. You know what? I'm going to stick with t. I like t more. That's just me. T approaches infinity. And if I throw that in, that is negative 1 over 0.001, which is 1,000, 1 over t to the 0.001 minus 1. As t approaches infinity, that will approach 0, and I'm left with a positive 1 over 0.001, therefore converge. So I take a limit. If the limit exists as a finite number, it doesn't matter what the finite number is. I'll say this integral converge. And that's pretty much it. If I look at the next problem, say, alright, well, let's see how this works. Here, I'm gonna let u equal radical x, or radical x minus 1, it makes no difference. So u squared equal x, and if I take a derivative, dx is 2u du. So this is the integral. That would be my u minus 1, and dx will be 2u du. And we dealt with this before. You could subtract 1 and add 1, or you could use long division, whatever makes you happy. This is twice the integral of, if I split this, u minus 1 over u minus 1 plus 1 over u minus 1 du. That is twice the integral of 1 plus natural of 1 plus 1 over u minus 1 du. So I do need that space. Let me move this out of the way. That would be twice u plus natural log of u minus 1. That's going to be twice. And if I substitute what u was, that was radical x plus natural log of radical x minus 1. And now I'm going to say, I'm going to integrate from 4 to t. And here, at this stage, I'm going to add the limit as t approaches infinity, right there. So this is the limit as t approaches infinity of twice the square root of t plus natural log of square root of t minus 1 minus, put a 4 in, that is a 2 plus natural log of 2 minus 1 is 1. That's a 0. That is, if I take the limit as t approaches infinity, square root of t approaches infinity, and natural log will approach infinity plus infinity, that will be infinity. Therefore, diverge. So if the limit is a finite number, it converges. If the limit is infinite, it diverges. Next problem up is number 10. That is twice. So this is one of the integrals that we agreed you're going to memorize. Times 1 over 2 the inverse tangent of x over 2. And I'm going to evaluate that from t to 2. But here I'm going to take the limit as t approaches negative infinity. That is the limit as t approaches negative infinity of inverse tangent of a 2 in there, that's a 1, minus inverse tangent of t over 2. That would be a pi over 4 minus. As t approaches infinity, the only graph you're responsible to know out of the inverse functions would be the inverse tangent. And if you remember correctly how this works, as t approaches negative infinity of inverse tangent, this will level off next to a negative pi over 2. No need to simply, you could say that's 3 pi over 4, but that's not going to matter. That's a finite value. Automatically, you would conclude there. Therefore, this integral converge. I'd like to look at number 56 next, and let's see how that plays. If you recognize what this is, that's good. If not, I would let x equal, it was the secant of theta, right? Dx is secant of theta, tan of theta, d theta. So this is the integral of that is secant squared of theta minus 1 dx is secant of theta, tan of theta, d theta. So this radical is the square root of tangent squared of theta, and that turns out to be just tan of theta. So this is the integral of secant of theta, tan of theta d theta, over tan of theta. Those cancel out, and I'm left with natural log of absolute value of secant of theta plus tan of theta, and I'm going to evaluate that from 2 to t and take the limit as t approaches infinity, but I do need the triangle. So if I draw my triangle, secant is hypotenuse over adjacent. That makes this the square root of x squared minus 1. And that's going to be, again, let me move those out of the way. That would become the limit as t approaches infinity of natural log, and let's see. Secant is x, tangent is opposite over adjacent, correct. Perfect. Evaluated from 2 to t, that is the limit as t approaches infinity of natural log of t plus the square root of t squared minus 1 minus natural log of, and that will be a 2 plus square root of 1. And as t approaches infinity, this and this will approach infinity, and that will make it infinity minus natural log of 2, which is infinity, therefore diverge. Next example, number 20. Well, here, if I let u equal inverse tangent of x, du is 1 over 1 plus x squared dx. So this is a simple u sub. That is 16. Add 1 to the power, divide by that. So that's going to be 8 times inverse tangent of x evaluated from 0 to t, taking the limit as t approaches infinity. That would be the limit as t approaches infinity of 8 into inverse tangent of t minus inverse tangent of 0 is 0. As t approaches infinity, that would be pi over 2, and that turns out to be pi over 4, and therefore it will converge. So the next problem up is when you have two infinities. Well, it's not really much, just a bit more work. If I glance at number 14, I notice that, well, this is a u sub as well. If I let u equal x squared plus 4, du is 2x dx. So this is the integral of, that's u to the 3 halves. X dx is 1/2 du. And this is 1/2 the integral of u to the negative 3/2 du. That is 1/2 times u to the negative 1/2 negative 2 over 1. That's going to be negative 1 over the square root of u, which is x squared plus 4. That's the integral. Now, as far as the limits, when I take the integral from negative infinity to positive infinity of x over x squared plus 4, 3/2 dx, I'm going to split this up. I'm going to say, you know what, this is the integral from negative infinity, zeros on that graph, plus the integral from 0 to infinity of x over x to the 4 plus 4 to the 3/2 dx. So this is going to be, for the first piece, negative 1 over square root of x squared plus 4 evaluated from t to 0, taking the limit as t approaches negative infinity, plus this is going to be negative 1 over the square root of x squared plus 4 evaluated from 0 to b, taking the limit as b approaches positive infinity. This is the limit as t approaches negative infinity. If I throw the 0 in, I'll get negative 1/2 plus 1 over the square root of t squared plus 4. So I'll take this. If this limit diverge, I'm done. But this will approach 0. I'm left with negative 1/2. That's accepted. Therefore, I need to do the second. If this integral was to diverge, I'll be done. In this case, it didn't. Limit as b approaches negative infinity of negative 1 over the square root of b squared plus 4 plus 1/2. This will also approach 0, so I'm left with 1/2, which is a finite number. Therefore, I conclude that this integral converge. And there's your homework.